All right. Welcome, everyone. Our next speaker is Kitsuya Azuma, who is going to present on Beyond Multiprocessing, a real-world ML workflow speed up with Python 3.13 plus free threading. Can we all welcome Kitsuya?
All right. Hello, everyone, and welcome. Thank you for coming. My name is Kitsuya Azuma, and today I'm going to talk about a major shift happening in the Python world. The title of my talk is Beyond Multiprocessing, a real-world ML workload speedup with Python 3.13 plus free threading. Just a little bit about me. I'm a master's student at Institute of Science Tokyo. My research is focused on federated learning and computer vision. I'm passionate about writing high-performance and robust Python code. And next year, I will start my career as a platform engineer. All the code and slides for today's talk are available from this single link. If you want to run the code or have the slides on your device, please scan this QR code. You can also find them on the PyCon JP websites. So let's start with the core question that shapes parallel programming in Python for years. How should we parallelize CPU-bound tasks on multiple cores? For a long time, the go-to answer was simple and clear: multiprocessing. It was the standard playbook. But today, I'm here to tell you that there's a new, strong contender in the ring: free threading. And it's time to reconsider our old assumption. If you remember only two things from my talk, I want them to be this. First, free threading makes threading a powerful and sometimes superior choice for CPU-bound tasks, especially when you are dealing with shared data. And second, the golden rule: measure, don't guess. Your workload is unique, and you have to measure to find out what really works. So what is this game changer? It is free-threaded Python. Just quick show of hands, how many of you have heard of free-threaded Python? Oh, almost everyone. And then how many have actually tried it? Oh, thank you. That's more than I expected. And to understand its impact, let's look at before and after comparison. Before, in standard Python, we had the global interpreter lock, or GIL. You can see it here as this red locked padlock. No matter how many threads you had, the GIL forced them into a single line, allowing only one CPU to use. Now in the afterwards, which is officially supported in Python 3.14, that lock is gone. So our thread can finally run in true parallel on multiple CPU cores. So what is it? It's an official, but still optional way to run Python without a global interpreter lock. And what does it mean? It means finally we have true parallelism with our threads. As you know, in this conference, there are many talks about free threading. The morning session covered the internals of the GIL, which was very interesting. And in my talk, I will focus more on the practical applications. So here's our path for today. I've broken down this journey into 4 clear steps. First, we'll cover the basics for a quick recap of concurrency. Second, we'll dive into the evidence with head-to-head benchmarks comparing threading versus multiprocessing. Third, we'll enter the real world. We'll show you how I apply these techniques to a demanding machine learning workloads. And finally, we'll build your playbook, a practical guide to help you choose the right tools and avoid common pitfalls. So let's begin with the first section, the basics. Before we dive in, let's quickly align on two key terms, concurrency and parallelism. They are often confused, but they are not the same things. I find the distinction is beautifully captured in a famous talk by Rob Pike, who is one of the co-creators of Go. He explained it like this: concurrency is about dealing with lots of things at once, but parallelism is about doing lots of things at once. So keeping this distinction in mind is key. Next, process versus thread. A process is an executing program with its own independent memory space. So think of it as a separate house. A thread, on the other hand, lives inside the process and shares memory space with other threads in the same process. They are like roommates in the same house. So this difference is critical because thread shares memory space. Communication is fast and cheap. No serialization needed. But with process, sharing data means high overheads, packing it up, sending it over, and unpacking it. This is a bottleneck we are aiming to solve today. So back to the Python words. Free threading fundamentally changed the game. This table shows the new landscape. With Gil, here, threading was only concurrent and best for IO-bound tasks. But in free-threaded world, it becomes truly parallel and a strong contender for CPU-bound tasks. It maintains its key advantage, shared memory space, and low overheads. This puts it in direct competition with multiprocessing, which is also parallel and good for CPU-bound tasks, forcing us to ask, which is better and when? Okay, so we've set the stage and introduced our contenders, but theory will get us only so far. To see which approach really wins, we need proof. That brings us to our next chapter, the evidence, where I'll let the number do the talking. And this is our proving ground, the setup for benchmarks. The machine, a powerful server with 32-core CPU and 128 gigabytes of RAM. Plenty of cores to push our contenders to their limits. Next, the Python version, we use 3.14 RC2, comparing the Geo build against the new free threading builds. Finally, the goal is simple, to compare threading versus multiprocessing on demanding CPU-bound tasks and see what the new landscape really looks like. Our first test is pure CPU-bound task, counting prime numbers up to 10 million. The logic is simple. We split the range of numbers into chunks, and each worker counts the primes in its assigned chunk. Finally, we aggregate the results. This is an embarrassing parallel problem. There's no data sharing between workers, just raw computations. This is the ideal scenario for multiprocessing. The question is, how will free-threaded threading compare? And here are the results. Remember, execution time is on the y-axis, so lower is better. And number of workers, in other words, degree of parallelism, is on the x-axis. First, look at the solid blue line, traditional threading with Gil. Just as we'd expect, it doesn't scale at all, or even get worse as we add more workers. The Gil is a hard bottleneck, and this confirms what we've experienced for years. Now let's look at other three lines. I know they are basically overlapping, which is hard to see, but yeah, that's actually the most exciting part of this graph. We see multiprocessing in orange line, scales beautifully as we add more workers. This is classic high-performance solution we've always relied on. But the amazing part is this, the dashed blue line here. For free-threaded threading is right on top of it. It's tracking multiprocessing performance almost perfectly. This historical gap that has defined Python parallelism for decades is gone. So the key takeaway here is clear. For pure parallel work with knowledge sharing, free-threaded threading is now just as fast as multiprocessing. Okay, on a simple task, it's tie. But real-world application almost always involve data sharing. This brings us to our second case, CPU-bound task with data sharing. The task is to sum a giant NumPy array with 100 million elements. Right? The workflow is similar with the last case, but with one key difference. Now all worker needs to access the same initial array. So the cost of passing or sharing the large chunk of data could become a new bottleneck. This is where things get really interesting. Now let's take a look at the results. The table have completely turned. Notice how multiprocessing methods in orange or green lines flattens out due to its overheads. In contrast, the free-threaded threading in dashed blue line keeps dropping, making it the clear winner. The reason is simple. Threads share memory by default. This means almost zero overheads for data sharing, no expensive copying or serialization. So the key takeaway here is with shared data, threading's low overheads gives it a powerful advantage, making it a superior choice. Okay, so we've seen the raw numbers on synthetic benchmarks, but how does this translate to the real-world complex applications? This brings us to our third section, the real world, where we'll apply this technique to demanding machine learning workloads. The workload is a simulation of federated learning, which actually happens to be my research field. It might sound complex, but the basic idea is quite simple. Imagine if you want to train a powerful global AI model using data from everyone's smartphone, but without collecting their private data, like photos or messages. Federated learning makes this possible. Please look at this figure. Each client trains a small local model on its own data, and the server just collects all those models and average all of them. By doing this over and over, we can create one strong model without ever seeing everyone's private data. But of course, testing this in real world with thousands of actual devices is difficult. So we, researchers, simulate this entire process in a single powerful server. This simulation is CPU and GPU bound task, since it requires rapidly switching models, training, and exchanging large models every single round. That's why I believe this is a perfect real-world test case for our contenders. The classic approach to realize this FL simulation uses a framework like Flower, which is built on Ray, a general-purpose distributed computing framework. Basically, it uses a multiprocessing model. For data sharing, it has a really clever solution. As you can see in this diagram, model parameters, as you can see here, are converted to data type like NumPy array, and it is stored in this huge in-memory object store. So as long as you convert to NumPy array, Ray can perform zero-copy reads. So this is a great optimization that avoids the expensive cost of copying and deserialization, which shows how powerful and well-designed this framework Ray is. However, even with this optimization, the overhead for scheduling tasks and managing this complex object store can still be a significant bottleneck, especially for fast and repetitive tasks we have in our simulation. So our solution, which we developed, is called BlazeFL. It's directly built on the standard library, threading module. In a free-threaded Python, we can use threads for true parallelism. As you can see in the diagram, these worker threads, represented by these wavy lines, all live inside a single process. Because they all share the same memory space, they can access the model parameters directly with true zero copy. The key advantage is minimal overheads. There's no serialization or data copying bottleneck to slow things down. So it's simple and fast now. For this benchmark, this FL simulation benchmark, we are using a slightly different machine with 4 GPUs. We are using Python 3.13, which was the latest version compatible with all libraries, such as PyTorch. The goal is to compare our threading-based BlazeFL against the most popular framework, Flower. We also include BlazeFL's multiprocessing variant as a baseline for comparison. All right, here's the results. First, let's take a look at the results when we use a lightweight machine learning model, which is called CNN. The results are dramatic. The process-based methods, Flower in green line and BlazeFL in the BlazeFL's multiprocessing variant in orange line. So both are process-based methods are significantly slower, as you can see here. The framework overhead of Ray and the cost of creating new process are very apparent here. In contrast, BlazeFL's threading mode in blue line is overwhelmingly fast. Its minimal overhead is a massive advantage for this kind of repetitive, fast task. Now, what if the task itself is heavier? Here we use a more heavier Resonate 18 model. The heavier computation basically allows a method to scale better because the actual work starts to hide some of the framework bottleneck. But even here, BlazeFL's threading mode maintains its lead, as you can see in the blue line. It consistently provides the best performance. The conclusion is clear. Even on heavier workloads, the efficiency of free-threading-based BlazeFL provides the best scalability and top-end speeds. So let's quickly summarize the evidence. In the first case, with no data sharing, free-threaded threading catches up to the multiprocessing. In the second case, with data sharing, free-threaded threading pulls ahead because of its direct memory access. And in the third case, our real-world ML workloads, a threading-based framework is a clear champion. Its minimal overheads leads to the best performance in this real-world complex situations. So we've seen the power and proof, but with great power comes great responsibility. That brings us to our final section, Your Playbook, where we will discuss how to use this new tool safely and effectively. Sharing a memory space is what makes threading fast, but it also opens the door to a classic problem like race conditions. A race condition is when multiple threads access shared data at the same time, leading to unpredictable and corrupted results. Why is this a bigger deal now? Because the GIL often hide this problem from us. With the true parallelism of free threading, race conditions are far more likely to occur and even bite you. Let me show you a concrete example. Here's a simple program where two threads each increment a global counter 100,000 times. The expected final result is 200,000, right? When running with GIL, the result is always correct, 200,000. The GIL protected us. But with free threading, the result is a complete mess. It's wrong and it's different every single time. Why? Because counter plus equal 1 is not an atomic operation. It's 3 steps. Read the value, add 1, and write the value back. Without the GIL, threads can interrupt each other between these 3 steps, causing updates to be lost. This is a race condition in its purest form. Fortunately, the solution is a fundamental pattern in concurrent programming. We need to ensure that the read, modify, write operation is atomic so that it cannot be interrupted. In Python, we do this by protecting the shared data with a threading lock. By wrapping the critical section here in a with lock block, we guarantee that only one thread can execute that code at a time. With this simple change, our code becomes thread safe and we get the correct result every single time. All right, this slide brings me back to my second key message. Measure, don't guess. Don't optimize without data. Also, it's important to know the difference between benchmarking and profiling. Benchmarks, as we did, tell you what is slow. They measure total execution time to show which high-level approach is faster. On the other hand, profiling tells you why it's slow. It looks inside your code to find the true bottleneck. Is it a specific function or memory allocation, or maybe lock contention? However, unfortunately, there's another challenge in Python. Many popular profilers for Python, like scaling or PySpy, relied on the GIL internals. So they don't work with free-threaded Python yet. The solution is to use system-level sampling profilers, like Samply. These tools sample the code stack of your program from the outside at a fixed interval. So the tools like Samply is independent of the GIL. This allows you to find the bottleneck even in a free-threaded world. So with all these options, how do you choose the right tool? Here's a simple guide. Is your task I/O bound? Just use async I/O or traditional threading. Is your task CPU bound? The next question is, does it require heavy data sharing? If yes, start with free-threaded threading. It's likely to be your fastest option. If no, then multiprocessing and free threading are both great options, I think. You should benchmark them though. Finally, if you need to scale across multiple machines or clusters, then you need a distributed framework like Ray, Dask, or Horobot. All right, let's wrap up with the final takeaways. First, the GIL era is almost ending. For data-intensive single-node tasks, free threading makes threading a first-class citizen for parallelism, and it's often simpler and faster than multiprocessing. And second, measure, don't guess. Always benchmark and profile your codes to find the real bottleneck before you start optimizing. All right, thank you very much for your attention. I'd be happy to answer any question. Nihongoでも大丈夫です。
Any questions?
Thank you for a great talk. Threading is faster because it can share data, right?
Yeah.
And also, you said Ray share data with some central object store through shared memory,
Yeah.
right? So it also sounds like they can share data without serialization. So can you explain why still, multiprocessing the overhead is higher?
Yes, thank you for asking. That's a good point. Yes, Ray don't need data copying or deserialization, but you have to serialize those objects to put those objects into the in-memory object store. And yeah, that's the first point. And second point, Ray is still process-based model. So there's a cost to create a process for those so-called Ray actors. So if you have heavy workloads, Ray is a perfect option. But if you have lightweight workloads, then the object store managing or task scheduling could be the bottleneck. Does this answer the question?
Yeah, thank you.
Thank you. Sorry, could you turn on the mic?
Thanks for your talk. And have you heard about virtual storage in Java's implementation?
In Java's implementation?
Yes.
Sorry, I didn't have Java experience.
Yeah, but because there is actually an ongoing discussion about virtual storage in Python. So do you know anything related to that?
I'm afraid I don't. Sorry.
Okay.
Hi.
Hi.
So with the new free threading, if I get a deadlock, like, are there any tools to debug where it is?
Yes, thank you for asking. Also, that's a good point. I only mentioned race conditions, but there's still deadlocks. But deadlock is a common problem in both GIO builds and free threading builds. So, yeah, and to answer your question, I think CPU profiling tool for Python some of them can detect those deadlocks. So I recommend using this.
Okay.
Thank you for the presentation. So there's a lot of this concurrency, exciting stuff coming in Python. I don't know if you've seen, you mentioned the concurrent interpreters, which is a multi-interpreter in the same process. So it's kind of like a different model. Have you seen that, and how would you compare that with the different models that you presented here?
Thank you. I think that's an interesting question. Just before this talk, I asked ChatGPT that question. And yeah, with sub-interpreters, it's like the between of multiprocessing and threading. So it doesn't share the memory space, right? But it can be clean, just like as process. And anything else? Sorry, I forgot other points, but yeah, I think the strong point of threading compared to the sub interpreters is like sharing the memory space, so you can direct access to the objects.
Yeah, I think we are right. Okay, we can take one last question because we're running short of time.
Thank you. And then I can say I appreciate such a great work that finally make a threading to be like to be able to process heavy load. So, and I noticed that in your performance benchmark that it seems like that, yeah, something like this. After 16 cores that the performance speed up kind of got flat. Would you comment on that?
Yes. Yeah, that's a good point. I think, in my opinion, I haven't investigated into it, but I think it's the upper bound of CPU or like overloads. So yeah, I think it's not CPU, the CPU problem. Yeah. So there are too many models on single GPU. So, yeah, let's talk about it later.
All right. Thanks again for the wonderful talk, Kitsuya Azuma. Can you all give a round of applause for him?